For my lab, I took a video of my Jeep moving down a hill. During the filming, the camera did move slightly, so in order to account for that, I took a large frame sample, 200 frames between frame 400 and frame 600, which gave me the most accurate velocity value I could possibly have. The force in my video moved in the positive X direction. I used the decal on the side of the Jeep as the average position, as it gave me a easy target on which to mark my position throughout all the frames of the video. The scale was set to 4.4 meters, as I could easily measure from the front to the back of my Jeep, which was that length, and the total time for the segment was 6.5 seconds. As you can see, the average position is slightly off from the x-axis of the graph. That is due to the shakiness of the camera, and I tried to account for it as best as possible by sloping the axis at a negative 2.5 degree angle to both account for the hill and to account for the shakiness of the camera. This was then modeled in Python, where the mass of the object was determined to be 1,969 kilograms. The initial position was 0, due to it being the origin. The initial velocity was 1.109, which was calculated from tracker using the position divided by the time. The delta t was small compared to the total 6.5 second time frame at 0.01. And since the final velocity must be the same as the initial velocity, F net must equal 0, so I set that to 0. The total time was also set to less than 7 seconds to put in the parameters of my video. Finally, Newton's second law and the fundamental momentum principle were applied for the other variables. And when I run the program, you can see the ball starts at the origin, moves in the positive x direction. Here you can see the plus x, the time against the position, which shows the velocity, where the position ends at 7.7 and the time ends before 7 seconds. This was then compared to the original tracker model with a graph in Excel. The blue line is the tracker model, and the red line is the vital model. And as you can see, they're very, very close to each other, and in the end produced around the 1.1 meters per second that I had gotten with the tracker. In order to get the most accurate data possible, I made a few assumptions. One of these was that there was no force in the y or z directions. This meant I could focus solely on the x direction, not have to worry about any other variables. Another one was that the object, which in this case was the Jeep, was moving at a constant velocity. What if I change the origin? Well, if I change the origin, the initial position will obviously change, as is indicated here, where I change it to -1. However, even when you change the initial position, the total distance traveled still stays the same, although the ending region is different. As you can see here, it started before the origin, moved across from it. You got the same distance total on the same time. What does it mean? How many pusher poles are added to give a zero net force? This is very complicated with my model, as I used a vehicle, thus there are many variables that come into play. But if you put it basically, there'd be one push and one pull, which would counteract each other to give you the zero net force. The push would be gravity, and the pull would be the brakes slowing it down. And that's my lab. Thank you.